right, so in chapter 17, we're going to be talking about acid and base equilibrium. So very similar to chapter 16, but in this case, we're talking about the weak acids and weak bases when they go through their equilibrium equations, which means their partial ionization, kind of like we learned in Chem 1. So just a general, just ideas of acids and bases. We have stomach acids, which help break down our food, and our stomach enzymes secrete hydrochloric acid. And our stomach lining is very pH insensitive, really. I mean, it could operate at very low pHs, and it really helps break down our foods. And also the enzymes like trypsin. Trypsin is an enzyme in the stomach that helps break down our food, and it operates at a pH of 3.2 or around 3 range. So it's a very acidic environment enzyme. Most enzymes in our body, they operate well at pH 7.4, which is our blood pH level. But it depends on where in the body it is. So in order to, let's say you have too much acid, let's say you eat something that doesn't agree with you, or you eat something, too much meat that that maybe wasn't cooked well, or your body isn't used to that type of spice or that type of meat. What'll happen is you'll get heartburn, which is you get an over excretion of this acid because your body doesn't know what to do and how to handle this new food. So it's going to release more acid in order to try to break it down. But in releasing that acid then builds up and starts to go near the esophagus, and you start to feel a burning sensation, right? And that's what we call acid reflux or heartburn. And it's not really anything to do with your heartburn. When I was little, I thought it had to do with your heart, but no, it doesn't. It just feels like your esophagus is behind your heart or adjacent to it. So it kind of seems like that. But your esophagus lining is not like your stomach lining. It can't really process, or the lining of it doesn't like acids, whatever, for better sense. It's not acid resistant. And we have a good question here. So why do certain foods cause heartburn? Because they are evil and they hate me. Okay, that works. That's a good answer. Well, it depends on the person. So like for some people, spices cause heartburn. But let's say if you're in like a lot of Hispanic cultures that have a lot of spicy foods, or even in Indian cultures do have spicy foods, then they're used to it because they've been eating it since their whole life. So it depends on what foods cause heartburn. Depends on, it's nature and nurture. Some of it's genetic and some of it is your cultural and what you're used to eating. So you could always, if you're trying to eat new things, then your body might not agree with some of the new things that you eat. And that's not because it's not good food. It's just because your body's not used to it. And well, it might go, so Brian, it might go away if you get used to the food, but if you have some kind of enzymatic intolerance to a specific thing, like some people, they don't like with lactose intolerant is kind of the same. Your stomach just gets, you don't have lactase, beta galactosidase enzyme to break down the glucose, to break down the lactose. So what that does is because you don't have the lactase enzyme, then your body tries to overcompensate by secreting a lot of acid in order to break down the cheese or break down the milk. So it's nature and nurture. So it's a really good question you have there. Okay, so properties of acids. The main thing that we're going to talk about when we say acids is they have a hydrogen that is deprotonatable, and protonatable, that means deprotonatable, meaning it can take the hydrogen off. So it's a compound that has a hydrogen that can be taken off. That's what an acid is. And this hydrogen, we're going to be talking about all class. We call it the hydronium ion when we mix it with water. Also just plain old H+. And that's how we determine pH of things. Is the pH is the negative log of the hydrogen ion concentration, or the hydronium ion concentration if the mixture or the reaction is in water. So and in terms of the chemical or the physical properties of acids, we have this: they taste sour, so don't go into a lab and drink hydrochloric acid. They can dissolve metals if they're at high enough concentrations, and they have ability to neutralize bases, and they turn the blue litmus paper to red. So litmus paper is a pH sensitive paper which can be used to determine the pH of any kind of solution based on the color that it turns, but don't really focus on that too much. What we're going to see for the acids is that here's an example, acetic acid, and it has hydrogens in it, but there's usually a hydrogen in the front. Wherever you see this hydrogen in the front, this means most likely it's an acid, and this is the hydrogen that will dissociate from the rest of the acid when it is reacted in water. So that's the hydrogen that would come off. Here's some common acids. We'll talk more about strong and weak acids in a second. And the structure of acids, so there's different types of acids. Acetic acid is an organic acid. There's some that are more what we call binary acids, so hydrofluoric acid, hydrochloric acid. You should be familiar with these names from Chem 1. Hydrocyanic acid has the cyanide anion, hydroiodic acid, things like that. And then there are these oxyacids, which are hydrogen paired up with a oxygen-containing polyatomic ion, which we've seen some of these: nitric acid, nitrous acid, sulfuric acid, phosphoric acid, perchloric acid, chloric acid, hypochloric acid, hyperchloric acid. So we've seen all those different types of acids last semester, and again, they have this hydrogen in the front that can be deprotonated, meaning it can come off in a neutralization reaction to neutralize a base. So any questions on that so far? This is kind of just a refresher. No? Okay. All right, so structure of acids, we have for the organic acids, they have this, the functional group, the organic functional group that makes them acidic is this carboxylic acid group. And it's represented by the covalent bonds of C double bond O. That carbon's also bound to a hydrogen or an oxygen and a hydrogen. And this is the hydrogen on the end, the one that's deprotonatable, the one that would be ionized when it reacts in water. So here's some examples of other acids. We have the H, they all have the H in the front, and at all times, only one hydrogen will dissociate at a time. Even though, like, we have sulfuric acid, which is H2SO4. When it dissociates first, the sulfuric acid is a strong acid, but only H2SO4 is a strong acid. When the hydrogen comes off, and that's what we call hydrogen sulfate, it's still an acid, it's a weak acid. But that second hydrogen won't come off as easy. So we'll talk more about that when we get into equilibrium. Okay, so any questions about the basics of acids? We're going to get more in depth, but any questions right now? No? Okay, so let's talk about bases. So bases used in a lot of cleaning products. Oh, we do have a question? Oh, the basics of bases, the basics of acids. So basically, bases, they taste bitter. Whenever you hear the word alkaline, usually it means something that's more basic, and it's really they're kind of poisonous, like alkaline batteries. Really can't eat that. Feel slippery, so a lot of soaps. They can neutralize acids, and they turn the red litmus paper blue. So it's kind of the opposite. And here's some common bases. Now, bases, the ones that you would need to know are the strong bases, which are the group 1 and group 2 hydroxides. And we'll get into this in a second, but just so you can hear some buzzwords, is we have the group 1A and 2A hydroxides, which are the strong bases. Ammonia is a weak base. That's one of the most prominent ones, and you've seen that a lot last semester. Sodium bicarbonate and sodium carbonate. Those are some solid weak bases as well, and that are used readily, and you see them often. Okay, so now we can talk about the certain historical definitions, which, I mean, they still hold true, of what an acid and a base is. So there was two main schools of thought. The first is the Arrhenius definition. So remember the Arrhenius equation? Well, look, this guy's back. And he is back, coming back with a vengeance. He loves acids and he loves bases, and he has ideas about them. So what he said is that acids produce hydrogen ions in a solution. And he's totally right. They do. And these ions, when they're in the solution and it's an aqueous solution that's water-based, they're going to react and associate with water. And they're going to create this hydronium ion. And we'll be seeing this a lot. And something that I want to mention is that once we see it, we want to consider them the same thing. This H plus is the same thing as H3O plus, which is the same thing as a proton. Yeah, Christina, he's brought back dangerous chemicals. Yeah, Arrhenius, he didn't like how you guys were making fun of his equation, and you didn't like his equation, but now he's like, oh yeah, well, I'm gonna burn you with some hydrochloric acid because it's a proton producer. So anyway, proton, that's the same thing as a H plus, and then in water, the H plus will associate with water and make H3O plus. So when we talk about pH, we talk about the negative log, and in Chem 1, maybe you've seen it, or in high school, you've seen it as the negative log of H plus. In today's chapter, we're going to refer to it as the negative log of H3O plus. Same exact thing. So don't freak out when you see those different definitions. I'll put pH equals. Okay, and then what a base does, according to Arrhenius, is instead of producing H plus, it produces OH minus. So these H plus and OH minus, they're antagonistic. They're the opposites of each other when we're talking about the strength of an acid and the strength of a base. And that'll come into play later. And I'll give you a hint of how, or a preview, that pH, why is it called pH? So the P, wherever you have a lowercase p next to something in chemistry, that literally means negative log. It's something in Latin, I don't know, but like it refers to the negative log. Like, kind of think of it as like a symbol. So what this means is P means negative log of H. So the negative log of the hydrogen concentration. There is also a thing called the POH, meaning the negative log of the OH concentration. And this is going to be kind of the opposite of the H concentration. I have a comment. Oh no, it doesn't mean percent hydrogen. It just means the negative log of the hydrogen, because it's not percent hydrogen. That's a good way to think about it, though. I mean, it's if you know it's not the real percent, you can think about it as percent. Fine, but yeah. But then it's still not, because then if your pH is high, that means you have a low percent. Like high pH means basic, which means not much hydrogen. So that's a kind of a slippery slope to think about like that. Yeah, but the proportion, it would be like the opposite of the proportion. So yeah, so yeah, whatever. I mean, you got this far with that, so that's good. So I don't want to ruin any associations you have in your head that make you think of the correct thing. So as long as you know the correct thing, you're good. Okay, so that's POH. We'll talk about that more later. All right, and then you have Bronsted, Lowry. There are two different people, and they came along and they were like, all right, another way to think about the exact same concept, that an acid produces H plus in a solution, is an acid donates the H plus. Doesn't just produce it in the solution. It has to go somewhere. It donates it. So they're saying that it donates it to the water, and that water becomes H3O plus. Where Arrhenius was like, it's produced, and then yeah, sure, it can go to the water, but it's produced first. Bronsted, Lowry just took it one step further, and they're like, it donates it, or the acid donates the proton to something else. Meanwhile, the base, accepts the proton. And this is a better, more general definition, because producing OH, that's true, but in some cases, a better way to think about it is, let's say we have H2O plus NH3 ammonia, right? You're adding a base to water. What happens is the base will accept a hydrogen, become ammonium, and release and basically leave an OH minus. So technically you can say the OH minus is produced, but a better way of thinking about it is the reason why it's produced is because the ammonia is a Bronsted-Lowry base, meaning it's a proton acceptor. It likes to take a proton from the acid, which in this case, the acid was the water. Water could act as an acid or a base. So there's a lot there, but does that make sense, or are there any questions on that conceptually? And we have one. Good so far. All right, let's keep it going. Okay, so here's another example of arrhenius acid where you have HCl. It dissociates when you add it to water into its H plus and its Cl minus. But in reality, what's happening is you're adding it to water, and the water is acting as a base. So the water will take the hydrogen, meaning it's a proton acceptor, and it'll become H3O plus the remaining chlorine anion. So that is the Bronsted-Lowry definition of what's happening. Not a simple dissociation, but it's actually dissolving in the water, and the water is neutralizing it as much as water can possibly neutralize something, which isn't much because it's a pH of 7, but neutralizes it a little bit. So we talked about the hydronium ion already. It's basically the same thing as H plus, but when H plus reacts with water and the water acts as a base, meaning it is a proton acceptor. And then here's an arrhenius definition of a base, where you have a base, remember, produces OH in solution. So Arrhenius was like, all right, it's simple. Sodium hydroxide becomes sodium plus and OH minus. But then Bronsted-Lowry was like, all right, actually what's technically happening is you're adding it to water. The water is acting as an acid. So the water is going to remove its hydrogen, and this gets kind of weird, but basically what happens is you end up with Na plus water and an OH. So it's not really, it's going to be kind of weird, but like, it'll be like that, kind of. It'll kind of produce, this example is not as good. I like Arrhenius better for bases, but you end up with 3 separate entities, because the hydrogen is not going to accept. It's not going to accept the water is not going to accept the hydrogen. It's just going to be there, and it'll try to donate its hydrogen to this one. But in doing that, you'll create water. So this water molecule, these water molecules are not the same. This original water gave its hydrogen to the OH. So it's like, here, I'm an acid. I want to help to neutralize you. Make water. What's remaining from this water after that hydrogen's removed? Just OH, which is right there. And then you end up with Na. So that's the Bronsted-Lowry way of looking at it. They're both correct, and it's basically the same thing. Yeah, exactly. Yeah, it's not going to neutralize by itself. So it needs, that's why when we do neutralization, we're always adding it to a water-based, an aqueous solution. It wouldn't just do it on its own. Oh no, there we go. That wasn't responding for a second. Okay, so when you have an acid-base reaction, the same thing happens, and just to a larger extent, where you, instead of trying to partially neutralize with water, you're fully neutralizing. So let's say HCl and NaOH. That's the most common acid-base reaction. What happens is in any acid-base reaction is, even if it's a weak acid and a weak base, to some extent, you're creating a salt and water. So what will happen here is this is the acid, this is the base, and then what will happen is the acid is a proton donor. It will donate its hydrogen. The OH will be donated as well. So that the base will, produce its OH, and then the H and the OH will go together. They'll create H2O. And then what's remaining is NaCl, which is our aqueous salt. So in another way to think about acid-base reactions, the cations switch, just like we saw for precipitation reactions, right, with net ionic equation, things like that, where the cations will switch. You can consider H plus a cation and Na a cation. If they switch, you get the same thing. So that's another way to think about an acid-base reaction. Okay, so here's Bronsted-Lowry theory. We already kind of talked about that a little bit. So again, an acid is a proton donor, and the base is going to be the proton acceptor. So the acid will donate its proton to the base molecule. Because if you think about it in terms of the energetic favorability when you go into solution, what that means is acids don't want to be acids. They don't want to have all this hydrogen and be acidic. It's not good to be acidic. Everybody wants to be neutral. So in order to not be acidic, when exposed to water, the acids want to release their hydrogen, and the bases want to release their OH, or they want to gain a hydrogen in order to make themselves more neutral. So this is what Bronsted-Lowry was talking about. And here we go with this equation. We have HA, which is just a random acid. So H is the hydrogen that gets deprotonated. A is the acid part, plus B, which is a base. So what will happen is the hydrogen will be donated to the base, and it'll create what we call the conjugate acid, or the conjugate base. And then you'll create the conjugate acid of the base. So that's probably where we're going to go. That's where we're going to end up today, like 5 more minutes. We'll talk about the amphioteric and then conjugates. So amphioteric, that's a fancy word for basically what water is. Water can act as both an acid or a base, depending on what it is paired up with. So water is very chill. In other words, if it's introduced to HCl, HCl is like, hey man, I really need to get rid of this hydrogen. It's been bothering me all day. Water's like, yeah man, I'll take your hydrogen from you, no problem. And then this reaction will happen. And water will act as a base, meaning a proton acceptor, like this. But then if a base comes around and it's like, hey man, I need hydrogens. I don't have any. I really need them. I need to buy lunch. I need hydrogens to buy lunch. Water's like, yeah, sure, I can give you some hydrogens, no problem. And then the base acts as a proton acceptor. And it becomes NH4 plus, and then you're remaining with your OH. Yeah, water's a real homie, exactly. He's so chill. He goes along with everything, and he's cool. Cooler than me. All right, so we kind of talked about that already. Now the last thing we'll talk about for today is conjugates. So we'll just revolve around the same concepts again. And another thing, yeah, Sebastian, you're right. Everybody loves water. So like, that's another reason. That's why everybody loves water, because he's so chill, or he or she is so chill. They just want to help everybody out. Okay, so conjugate acid-base pairs. This is very simple, but I can guarantee you questions on the homeworks, on the exam, may ask you, what is the conjugate base of this in the reaction? What is the conjugate acid of this in the reaction? A conjugate pair, that represents one of the compounds that has the hydrogen, the other one that does not have the hydrogen. So for example, if you look here, NH3 and NH4 plus, that is a conjugate acid conjugate base pair. The before and the after product. Yeah. So Rebecca asked what exactly is the exchanging. So it's, you can look at the conjugate system as the before and the after. In either way, it could be reversed, just like these equilibrium reactions, but it's the before and the after, or the after and the before, however you want to look at it. But basically, NH3 is a base. When you add the hydrogen to it, meaning when it's reacted in water, it becomes its conjugate acid. Ammonia's conjugate acid is ammonium. Ammonium's conjugate base is ammonia. So if I asked you, what is the conjugate acid of water? So if water is the base, what is its conjugate acid? Good, H3O plus. Right? And then if I asked you for water, what is its conjugate base? That's what we have here. It would be OH because you're removing that hydrogen. And water could do both, as we mentioned before. It's amphioteric. That's why it can have a conjugate acid and a conjugate base. But for something like HCl, we know HCl's conjugate base is just Cl minus. But I'll write here, conjugate base. HCl does not have a conjugate acid because it can't get more acidic. It's a very strong acid. H2Cl is not a thing. So that's why that's one representation of it. All right, so are there any questions on the pairs, on basically what they mean? And we can do more examples in a reaction like this. So here's a reaction with ammonia and water. So here you have ammonia is the base, water is the acid. Ammonia's conjugate acid is the ammonia form when it gains the hydrogen. So it's NH4 plus. H2O is an acid. Its conjugate base is when it loses that hydrogen, meaning when it becomes OH minus. And it's the same thing every time. So if for right now, if you like, we'll do an example. What is H2SO4? What's its conjugate base?
H3SO4?
Its conjugate base, not acid. So to get to a conjugate base,
H1SO4.
Good, yes. We're removing a hydrogen to get to a base. Because the more hydrogens you have, the more acidic you are. If you want the conjugate base, you're removing a hydrogen. So H, and also keep in mind, a lot of you, you're saying the correct answers, but you're not including the charge. So H2SO4, it's neutral for a reason. The reason why it's neutral is because each H is +1 and SO4 is -2. But now, hold on, there's a question. Okay, yeah, good, HSO4 minus. Right, so now the balance of charges is not +2 -2. Now there's only one hydrogen, so it's +1 -2. So it would be HSO4 minus. That would be the conjugate base. Sumi, that was a good one. You don't have an extra hydrogen? How basic. I like that. I'm going to use that.
Probably how I'm going to remember for the exam.
Okay, awesome. Good. So everyone write that down. Wow, you don't have a hydrogen? How basic. So basic. Okay, so now is a fun fact. So we know sulfuric acid is a strong acid, but this hydrogen sulfate is also, it's a weak acid, but it's also an acid. Even though, this is where it gets a little bit weird, even though it's the conjugate base of an acid, it's still an acid. It's a weaker acid, a lot weaker, but it's still an acid. There's another conjugate base of HSO4 minus. So what's the conjugate base for HSO4 minus? Anybody? I don't know. You're the only one here, so it's the only vocal. Yep, SO4 what? Right now it's minus. Good, 2 minus. Yep, you got it. Sulfate. It would be just sulfate. Good. All right. Oh, you guys got it too. Awesome. So something like H2SO4, what we call is a diprotic acid. What that means, and we'll talk about that more next week, but diprotic, 2 protons, meaning it has 2 levels of dissociation, the first hydrogen and the second hydrogen. Boom, second hydrogen. Good job, Rebecca. So second hydrogen is a lot harder to remove than the first hydrogen. And that's usually the case for all of the polyprotic acids. So even the weak ones like H3PO4, phosphoric acid, it gets exponentially harder to remove the hydrogens because they get more stable over time. So, or over hydrogen removal steps. So anyway, we'll continue. All right, so question, which pair is not a conjugate acid conjugate base pair? B, yes, B is correct. Because, so A, we have the CH3,3N, the CH3,3NH plus. That means this is the acid, that's the conjugate base. For B, H2SO4, H2SO3. Nope, we want changes in hydrogens, not changes in oxygens. And then this one clearly with the hydrogen. So correct, good job. All right, so we're gonna end after we talk about acid strength and I give you my little acronym. It's a strong electrolyte, meaning not practically all of the acid molecules, they ionize. So every HCl molecule you put in there into water, it's gonna ionize completely. Same thing with a strong base, it's gonna ionize completely. The weak acids, they only ionize in a small percentage. And the weak bases, same thing. They're both weak electrolytes. And the main part of this chapter is using what we know about ice tables and exploring these weak electrolytes, weak acids and weak bases, and seeing how much they dissociate. We can figure out the percent ionization. We can figure out what their pH is at a certain concentration, where for strong acids, we can figure that out by just taking the log of their concentration. But for weak acids, we don't really know how much of the conjugate base and the hydrogen ions are present when it reaches equilibrium. Now that we know about equilibrium, we can figure that out. So it's great. It's a lot of the same stuff we learned from chapter 16. Examples of strong acids. So I'm going to go through my acronym that me and my frat brothers invented in college. So we weren't going to parties. We were talking about chemistry and thinking about chemistry all the time. But here it is. So I'm going to write them all out. And then I'm going to say them. It's not perfect, but it definitely helps. Better than memorizing them. No, hit clo. His so. All right. And they're kind of in order here. But so Hickel, Hibber, High, Hino, Hiklo, Hiso. There's 2 Hiklos. That's the only like nuance. So Hickel, Hibber, High, Hino, Hiklo, Hiso. And I have that on my YouTube videos and also the 100 sub special, extra credit. I can do that. So Hickel, Hibber, High, Hino, Hiklo, Hiso. Now, if you need that to be repeated and you want to study it later, oh, thanks, guys. Thanks for the support. Really appreciate it. Wouldn't have got this far without you. Well, I get paid the same, but I wouldn't have as much fame. All right. Well, no, you're not going to lose me. I love teaching. Just subscribe. All right. All right. So if you want to hear this being said over and over again by me, I don't know why you'd want that. Go to Instagram and look up #CrashChem and look at my video I have for acids and bases, going over the strong acids and strong bases in 30 seconds. So when you're studying, you need to figure that out. You need to look at that. You guys are distracting. Smash that subscribe button. You don't have to turn on notifications. That's annoying. You could. I mean, it's in your best, at least during the semester you can. It's in your best interest, but afterwards, I don't care what you do. Okay, unless you want to see more videos of other classes I end up teaching. Okay, so Hickel, Hibber, High, Hinel, Cloiso. So HCl, HBr, HI, Hinel, which is HNO3, hydrochloric or nitric acid. Then you have perchloric acid, and then you have chloric acid. Then you have H2SO4, sulfuric acid.